Welcome to example number 3. Now we have an example where the bars are not kept in series but are kept in parallel. So a similar bar, same as what we had before, copper and steel, except now you'll notice they're side by side. And we want to know what is the total rate of heat flow between the two bars. So there's no intermediate temperature between the two bars in series because they're now in parallel. So now to calculate the heat flow for two bars held in parallel, it's really the sum of the two individual, or if there were 3 bars or 4 bars, really all the bars that are held in parallel. So the total heat flow would be the sum of the currents or in the 2 bars. So the heat flow through the steel plus the heat flow through the copper. Okay, and the equation we use for the steel is K for steel times the cross-sectional area times the change in temperature divided by the length of steel. And then we have K for copper, area times the change in temperature all over the length of the copper. Again, I believe we're not going to get 97.1 because I'm using a different thermal conductivity. From the earlier problem, steel we used a value of 14 and copper was 390. So we have 14 joules per second times meter times degrees Celsius. And then we have the area. We will use the same area we had before, which is 4 to the power negative 4 meters squared. The change in temperature is 100 Celsius now, because we know from this end to this end is just a 100 Celsius, and then divided by the length of the bar for steel is 0.1 meters. Then we have the same expression, similar expression for copper, 390 joules per second times meter degrees Celsius, and then 4 to the power negative 4 meters squared. 100 Celsius is the change in temperature once again for here, and then the distance is actually for copper is 0.2 meters. And for copper we have a value of 5.6 joules per second. Over for the actually that was for the steel, sorry, and for the copper we had a value of 78 joules per second. So you can see that this is a much better conductor here. Most of the heat is flowing through the copper section, or actually, yes, flowing through the copper section. And we get a total heat flow of 83.6 joules per second. So this needs to be just changed here. It's 83.6 watts. So once again, notice that the heat flow in the copper bar is much greater than the steel bar, even though the copper bar is longer. The thermal conductivity for copper is much larger, which means it's a very good conductor. So you might ask yourself, what kind of properties could I change in the steel to cause it to have the same amount of heat flow that the copper has? Say, obviously we can't change its thermal conductivity, and we can't change the change in temperature because it's the same temperature difference between here and here, and for copper. However, we could change the cross-sectional area for steel and make it much, much larger, and you could get almost the same heat flow as copper. Okay, and that's it for this example and our examples on conduction.